Welcome to Summarize Science, where we break down complex research for you. Today, we're looking at a fascinating paper that asks a critical question. Can the most advanced AIs actually think like a physicist on the cutting edge of research? Researchers created a new benchmark called CritPt, or critical point, to test the absolute limits of AI reasoning. This isn't about solving high school homework problems, which we know AI is getting good at. The goal here was to see if AI can tackle unseen, entry-level research problems that require original thinking to find a solution. Crucially, they also wanted to know if we can trust the AI's reasoning in a field where a single subtle error can invalidate an entire result. To do this, they designed the test to be incredibly difficult and, most importantly, leakage-resistant. This means all the problems were newly created by over 50 active physicists based on their own work, so the AI couldn't just find the answer somewhere in its training data. The questions are open-ended, and the answers are often complex numbers or formulas, making them impossible to simply guess. They also built a sophisticated auto-grading system that understands advanced physics notations to check the answers. The benchmark is incredibly broad, covering almost every major area of modern physics. This includes everything from quantum information and astrophysics to condensed matter and biophysics. So, how did the best AIs, including GPT-5, actually do on these full-scale, challenge problems? The results were staggering. The best-performing base model only achieved a 4% accuracy. Even when given powerful tools like a code interpreter and web search, the top score barely reached 11.7%. This chart clearly shows that nearly all current models score close to zero, highlighting how far they are from being able to solve complex research problems from end to end. But what if the problems are broken down into smaller, more manageable pieces? The researchers also tested the AIs on checkpoints, which are individual steps or simplified versions of the main challenges. This simulates how a human researcher might use an AI as an assistant for a specific part of a larger project. On these smaller tasks, the AIs performed noticeably better. The top model, GPT-5 with tools, managed to correctly solve about 25% of these checkpoint tasks. This suggests that while AIs aren't ready to be autonomous researchers, they might soon become useful assistants for more focused, granular steps in the research workflow. However, there's another crucial factor in science: reliability. The researchers introduced a stricter metric where a problem was only considered consistently solved if the AI got it right in at least 4 out of 5 separate attempts. Under this reliability test, the performance of all models dropped dramatically. This tells us that even when an AI gets a correct answer, it might not be doing so through a robust reasoning process, making it difficult to trust in high-stakes scientific applications. So, let's recap the important points. First, there is a huge gap between what current AIs can do and the deep, creative reasoning required for frontier physics research. Second, they show some early promise on smaller, well-defined subtasks, suggesting a future role as a physicist's assistant. And finally, their current lack of reliability is a major hurdle that needs to be overcome before they can be trusted with important scientific work.